In the world of aviation, companies are constantly innovating, and aircraft wings play a pivotal role in shaping the future of flight. From unconventional shapes to cutting-edge technologies, these wings are designed to test new ideas and creative concepts. Here are the top 15 most unique plane wing designs. Number 15. The X48 Blended Wing. The Boeing X48 is an experimental aircraft that was developed by Boeing in collaboration with NASA and was created specifically to try out a new wing design concept. The X48B model is a blended wing body aircraft, and its wings are a central element of its unique configuration. So much so that when you first see it, the aircraft doesn't even appear to have any distinct wings. Instead, it looks more like a flattened, oval-shaped fuselage. This, of course, is the entire point of the design, whereby the blended wing concept combines the fuselage and wings into a single continuous shape and offers several advantages as a result. The most important one is the improved aerodynamic efficiency by removing the drag-inducing seams and junctions that traditional aircraft have. Its configuration also allows for a larger internal volume compared to traditional aircraft of similar size, which could potentially be utilized for various purposes such as cargo carrying, passengers, conducting research, or housing advanced equipment. Additionally, the blended wing body provides greater lift and control, enabling the aircraft to handle a wide range of flight conditions effectively, and it improves its handling, which makes it an ideal performer for testing and developing new flight techs as a part of a wider development program. Only two small unmanned versions of the X48 with 21-foot wingspans were ultimately produced, and while test flights took place in 2007, the model has been retired. Lots was learned, though, about this type of configuration, and it is likely it will be replicated in the future experimental aircraft just to see how far it can be pushed. Number 14. The AD1 Oblique Wing. The Ames Dryden 1 Oblique Wing was an experimental aircraft that was developed in the late 1970s by NASA and the United States Air Force. The reason it was so interesting to them at that time was the concept involved an ability to change the sweep angle of its wings during flight, which in theory allows pilots to adapt to changing conditions and requirements. Known as an oblique wing configuration, it's unlike typical aircraft with fixed wings, and instead has ones that pivot, which allows them to be swept back at different angles relative to the fuselage. This dynamic wing sweep capability was designed to address a fundamental challenge that's faced in aircraft design, namely balancing the aerodynamic advantages of high-speed straight-wing flight with the stability and control benefits of lower-speed swept-back wing configurations. In other words, aerodynamic designs that work well during takeoff and at low speed will become a hindrance at high speed. So by adjusting the setup mid-flight, you can ensure the best flight profile at any part of the journey. In a forward swept position, the AD1's wings generate less drag at high speeds, enhancing its efficiency and speed. And conversely, in a rearward swept position, the wings provide greater lift and maneuverability at lower speeds, improving the aircraft's handling characteristics during takeoff, landing, and other flight phases. The ability to change the wing sweep angle in flight was achieved through a complicated mechanical system that allowed the pilot to control the wing position, adapting it to the specific demands of different flight regimes. This technology paved the way for improved performance and versatility in aircraft design. Now, the AD1 prototype conducted a number of test flights during the 1970s, which provided data on the advantages and challenges of this oblique wing technology. While the AD1 didn't become a production aircraft, its research significantly contributed to the development of advanced aircraft concepts, and it influenced later designs that aimed to optimize the trade-offs. Number 13. The M2F1. The M2F1, also known as the Flying Bathtub, was an extremely unusual aircraft that was developed by NASA in the early 1960s. It virtually did away with the idea of having wings altogether. It almost looks like the opposite of what you'd imagine an aircraft to look like. Made of a simple fuselage that resembles a bathtub or a sled, it lacks all of the typical wings and tail surfaces found on most airplanes. But this was the exact reason it was created. NASA wanted to test a body concept, which sees the fuselage itself being shaped to generate lift as it moves through the air. This design aimed to explore the potential for controlled flight without the need for traditional wings, and it was of particular interest to NASA as they had the potential to improve its aerodynamic efficiency and give higher maneuverability. Only one unpowered M2F1 was built as a part of NASA's lifting body research program, and it did need to be towed into the air by a ground vehicle or aircraft, similar to a glider, before being released into the sky. And while it might seem bizarre, this was one of the most important test programs in NASA's history, as it validated the idea of the lifting body concept in certain scenarios. It demonstrated that vehicles with wingless lifting body designs could be controlled and landed safely, even when re-entering the Earth's atmosphere from space, and would most famously enable the design of one of the most important vehicles, the Space Shuttle. Number 12. The Vought V173. The Vought V173, which is more commonly known as the Flying Pancake, was developed during the Second World War as part of a test program looking to create aircraft that would give an edge in combat against the enemy. Powered by a piston engine and propellers to provide thrust, as was typical of the time, designers took a completely different approach with the fuselage and wing shape, making it circular instead of being straight or swept back. This circular wing, which looked like a flattened saucer, extended horizontally from the center of the fuselage and was done in a way to try to tackle several aerodynamic challenges as well as offer a number of advantages. One of the main benefits of a circular wing design like this is the ability to provide a much larger wing area within the constraints of a smaller fuselage, which leads to increased lift and greater stability. The large wing area also gave it impressive low-speed capability, enabling it to take off and land at much slower speeds than traditional aircraft. The position of the propellers at the wing tips were clever too, as their placement on a circular wing helps reduce the effects of wingtip vortices, which are a source of drag in a traditional wing design. Of course, the V173 never actually went into production, with only one ever fully being built, but it did prove to be a valuable testbed to further understand different wing designs and the benefits that could come from improved low-speed flight characteristics. No other aircraft since has featured circular wings as extreme as this, but some have taken inspiration from the V173 to gain some advantages without as many of the drawbacks. Number 11. The Rockwell HMAT. The Rockwell HMAT, which stands for Highly Maneuverable Aircraft Technology, was an experimental aircraft from the 1970s that was created to further knowledge of high-speed aircraft and help with building fighters of the future. Developed by Rockwell International in collaboration with NASA, the HMAT was packed full of the latest technological advances and ideas, such as close-coupled canards, digital flight control, composite materials, and synthetic vision systems. It was also designed with far more complex wings than normal, with various control surfaces and winglets added to show just how much can be changed in the flight profile to enhance an aircraft's maneuverability. Cleverly, HMAT was also designed in a modular fashion, which enabled certain parts to be changed or replaced during the testing program. And this all led to it in many ways being seen as one of the most influential test aircraft ever. That led to a number of common designs seen on the mass-deployed models that are flown today. With only two built, both of which were at 44% scale, they remotely operated so as not to risk pilot safety, and this allowed them to be pushed far further than would otherwise be possible. In the end, it was decided that the wing setup was too over-engineered for the benefits that it was giving. But you still see some of the newer generation fighter aircraft designs looking similar to this wing setup in ways, which shows how ahead of its time the HMAT may have been. Number 10. The Su47 Barut. Developed in the early 1990s, the Sukhoi Su47 Barut looks very different to most other aircraft because of its wing design, and was given its name, which translates from Russian to mean golden eagle because of the way that this allows it to soar through the skies. Almost looking as if the wings have been put on the wrong way around, the majority of fighter jets feature wings that are swept backwards, but the Su47's wings sweep forwards towards the nose of the aircraft. This unique configuration was chosen to leverage the potential advantages it could offer in terms of performance and maneuverability. One of the main benefits of a forward-swept wing design like this is the ability to provide greater agility at both subsonic and supersonic speeds. It enhances the ability to maintain control at high angles of attack, allowing for extreme maneuvers in dogfights and close combat situations, and that makes the Su-47 a formidable opponent. The forward-swept wings also delay the onset of wingtip stall, reducing the chance of a spin or loss of control during aggressive maneuvers, and further allowing the Su-47 to operate effectively and for longer at higher angles of attack even in challenging situations. To overcome some of the downsides associated with forward-swept wings, such as increased structural stress and aerodynamic instability, the Su-47 incorporates advanced material and sophisticated fly-by-wire control systems. It's not just the wing design that's advanced though, as the Su-47 features other cutting-edge tech, including small forewings for increased control and maneuverability, as well as a powerful engine which enhances its speed, making this overall a highly impressive aircraft. It was, though, only built as a tester, so only one was ever completed, but things that were learned from the design have been incorporated into Russian aircraft ever since. Number 9. The Caproni CA60. In the early days of aircraft design, engineers hadn't yet discovered the best and most effective ways of creating lift. And without computers to test models on, the only way they could figure out what worked was by building their creations. This led to a wide range of strange concepts, but perhaps none as unique as the Caproni CA60. Also known as the Novaplano, it was designed and built by an Italian aviation pioneer, Giovanni Caproni, in the early 1920s, and was a massive seaplane that he hoped would become a transatlantic passenger aircraft. As soon as you first see it, you notice something that's very different to planes that take to the skies today, and that's why it had 9 sets of wings arranged in a multi-plane configuration, with each set comprising 2 wings, one above the other, and placed to the sides of the fuselage. These wings were paired in 3 rows, with the top row featuring 2 wings and the middle row with 3 wings, and the bottom row with 4 wings, and an arrangement that resulted in a total of 18 wings. Caproni's choice of a multi-plane configuration with a multitude of wings was driven by the belief that it would provide enhanced lift and stability, making it possible for the CA60 to carry large numbers of passengers across the Atlantic. However, this ultimately proved to be overly complex and challenging to control. The CA60 was intended to have a wingspan of approximately 320 feet, which would have made it one of the largest aircraft of its time. Despite these lofty ambitions and only one actually being built, the aircraft never actually successfully flew. During its first taxiing test on Lake Maggiore in Italy in 1921, the CA60 experienced stability issues and capsized. This incident caused significant damage, and rather than trying again, the project was abandoned. Number 8. The McDonald Douglas X36. The McDonnell Douglas X36 was an experimental aircraft that had a particularly unusual wing design. It was developed in the late 1990s as part of the U.S. military's efforts to explore new ideas. The X-36 was designed to investigate the feasibility of tailless aircraft for enhanced maneuverability and also for ways to reduce an aircraft's radar cross-section so it was far more difficult to detect. It had a delta wing, which is a triangular wing shape without any horizontal or vertical tail surfaces. Now, for this to be feasible, innovative engineering solutions were needed to maintain stability and control. And to achieve this, the aircraft relied on a combination of thrust vectoring and control surfaces on the wingtips. The thrust vectoring system allows the X-36 to direct engine exhaust to control pitch and yaw, while small movable surfaces at the wingtips control the roll. This was all worth it, though, because the wing design contributed significantly to its agility. The aircraft was capable of executing rapid and precise maneuvers, including high angles of attack and extreme rolls, making it a valuable platform for researching enhanced capability from military aircraft. As a test aircraft, the X-36 was remotely piloted, allowing researchers to safely put it through its paces without risking any humans. And during its first flight testing program, it conducted 31 successful flights. Things were looking promising for further development of the project, but the X-36 itself has been retired for more than 20 years. Only 2 were built, which are now on display in museums, but many of its attributes have been included in the design of next-generation fighters, which are patrolling the skies today. Moving on to number 7, the X59 Quest. There's a problem in the aircraft industry that, for the moment, limits how fast planes are able to fly. Despite, in the Concorde, there have already been a supersonic passenger jet and plenty of military aircraft that are able to fly faster than the speed of sound too, breaching this barrier creates a sonic boom that can have serious impact on the communities at ground level. It's because of this reason that in the US and a number of other countries, planes are not allowed to exceed the speed of sound unless they're over water or if they're responding to a national security event. If, though, it's possible to develop a supersonic aircraft that doesn't create a sonic boom, then these limitations could quickly be overturned. The X59 Quest, which stands for Quiet Supersonic Transport, is currently being developed by NASA, along with Lockheed Martin, to try and do just that. It features a number of unusual design elements in order to do so. It, for example, has a unique wing design that sets it apart from traditional supersonic craft, where instead of the familiar delta wing or swept wing configuration, it has a slender, highly swept wing design. This design choice was driven by the need to reduce the sonic boom, as the shape and characteristics of the wings significantly impact an aerodynamic performance and noise generation. This slender design is optimized to minimize shock waves generated by the aircraft as it travels at supersonic speeds. The hope is to create a softer sonic thump or an N wave instead of a loud and disruptive sonic boom produced by older supersonic craft. The specific wing shape, combined with other aerodynamic features and advanced tech such as the long fuselage, the sloping cockpit, and a pointed nose, and carefully placed inlet and exhaust systems help spread out the shock waves, resulting in a quieter and less disruptive sonic profile. And where it does produce noise, it's done in a way that sends it upwards towards the sky instead of towards the ground. Still in development, it is quite possible we'll see aircraft like the X59 Quest flying at supersonic speeds over populated areas within a decade or so, vastly transforming passenger flights and the time it takes to travel from place to place. Number 6. Bartini-Beriev VVA-14. The Bartini-Beriev VVA-14 was an experimental Soviet aircraft that was developed during the Cold War era. Rather than being a typical fighter aircraft, it was designed to be a vertical takeoff amphibious aircraft that could operate effectively in both air and water environments, and as such has a number of design choices unlike anything else. The most notable element of it, though, is its dual wing configuration with two sets of wings. The upper wings serve as traditional airplane wings, and the lower wings act as hydrofoils for waterborne operations. The upper wings featured a forward-swept wing design that has a high aspect ratio, which itself was an unusual choice at the time. It was chosen to improve lift and control during flight, especially at low speeds and high angles of attack. The lower wings, on the other hand, were equipped with pontoons that could be deployed to allow the aircraft to float on water, and when operating on water, hydrofoils would provide stability and reduce the water resistance, enabling the aircraft to perform like a hydroplane. The ability to transition between flight and waterborne modes was a novel concept that offered potential advantages for amphibious missions and could, in theory, be useful for roles such as anti-submarine warfare, reconnaissance, search and rescue, and transportation. There's no doubt that the VVA-14 demonstrated its unique capabilities during a series of flight tests and waterborne operations, but the development project faced challenges and was ultimately canceled due to technical difficulties, budget constraints, and changing priorities. Essentially, while it was able to change between airborne and waterborne modes, it wasn't an improvement on specialized vehicles that already existed, and this adaptability in itself wasn't enough of a benefit to make further development worthwhile. Number 5. The Routan Very-Ease. The Routan Very-Ease is a small, unconventional aircraft that was designed by Burt Routan in the early 1970s. It was one of a series of home-built aircraft created by Routan and his company, Routan Aircraft Factory, and at least 400 of them were sold to enthusiasts to build themselves. Now, beyond the novelty of being able to build a fully functional aircraft in your backyard, Routan had to design the Very-Ease in a way that would make this affordable. So in doing so, he opted for a canard wing design. In a canard configuration, the aircraft features a smaller wing at the front, known as the canard, and a larger wing at the rear, which acts as a main lifting surface. This layout is the opposite of conventional aircraft, where the main wing is located towards the front and the tailplane is at the rear. On the Very-Ease, this design choice serves multiple purposes. Firstly, it generates lift like the main wing, but also helps to control the aircraft's pitch. And then it also provides increased stability and better stall characteristics, making the Very-Ease a much more stable and therefore safer aircraft for less experienced pilots to fly. This doesn't mean, though, that it lacks in speed, as the main wing, known as the supercritical wing, has a distinctive airfoil shape that's optimized for even high-speed flight. This design, combined with the canard configuration, allows the Very-Ease to achieve surprising cruise speeds up to 165 miles an hour with relatively small engine power, and the high aspect ratio wings help with the aircraft's fuel efficiency and performance. The wings, too, give the Very-Ease a short takeoff and landing capability, allowing it to operate in confined spaces, and not necessarily needing a runway, which further enabled hobbyists to see this as a serious option for personal transport. By using strong materials that were in many ways ahead of their time, the Very-Ease was an impressive attempt at a home aircraft, and only didn't go on to be more popular because of the need for a pilot's license to be able to take it into the skies. Number 4. NASA Helios. One of NASA's goals is to push forward the technological development of new types of aircraft, and one of the most radical one in recent years, undoubtedly, is the Helios. This solar-powered aircraft was designed to explore the feasibility of high-altitude, long-duration flight while relying solely on renewable solar energy, and crucial to this concept was its wing design, which had to simultaneously optimize lift and capture solar energy. It was their high aspect ratio that defined their shape, which is the ratio of a wingspan to wing area. In case of the Helios, the ratio was exceptionally high, and it was a design choice that was made to enhance its lift efficiency, particularly at high altitudes, where the air is less dense. The extended wingspan of 247 feet provided the essential lift needed to sustain flight while minimizing energy consumption. Now, this lightweight structure of the wings was another important factor due to the importance of weight reduction in any aircraft design, but particularly one where energy usage needs to be kept to a minimum. To achieve this, the wings were crafted using advanced materials, particularly carbon fiber composites, all of which offer an impressive strength-to-weight ratio. As well as being responsible for maintaining lift, the upper surface of the Helios prototype's wings were covered with a huge solar array made up of a thin film solar cell. Now, these were highly efficient at capturing solar energy and converting it into electrical power, so much so that during daylight hours, this solar array served as the primary power source for the aircraft's electric motors and systems, and was able to charge the onboard batteries to enable nighttime flight when solar energy was unavailable. High-altitude flight also poses a number of other issues, such as increased stress on the wings, which meant that these ones needed to be made as flexible as possible so they could bend and twist while maintaining their integrity. Now, amazingly, the combination of high aspect ratio wings and solar-powered propulsion system granted the Helios prototype the ability to reach and sustain high altitudes, often exceeding 60,000 feet. With the added benefit that operating at these high altitudes positioned the aircraft above most weather systems and provided access to even more sunlight, which increased its energy generation. Of course, technology like this isn't ready to create new passenger aircraft designs, but it shows the principles are already there, and in the future, wings like these may become more common as manufacturers try to make flight as energy efficient as possible. Number 3. The Douglas X3. The unusual-looking Douglas X3 Stiletto was developed in the early 1950s to explore high-speed flight and advanced aerodynamic concepts. And while its strange wing design wasn't the primary focus of the project, the X3 featured wings that were particularly radical at the time. It was its swept wings with an angle of 35 degrees that were considered aggressive for the era and were chosen with the aim of reducing overall drag and to delay the onset of compressibility effects at high speeds. The other new design element in the wings was their thinness, with an aspect ratio of 12.5 to 1. Thin wings like these are known for their aerodynamic efficiency at high speeds, particularly in supersonic flight, so they would enhance the other technological updates in the craft to push it as far as possible. Unlike other aircraft with delta wings of that era, the X3 also featured straight leading edges in order to balance high-speed flight capability with the need for control at lower speeds. But with its short wingspan of just 22 feet 8 inches, the X3 had a relatively small wing area, which combined with its thin wings made it less effective at lower speeds and less maneuverable than desired. Another unique feature of the X3's design was the integration of fuel tanks within the wings, which allowed the aircraft to carry additional fuel while preserving its sleek, slender appearance. This limited fuel capacity, though, posed challenges for long-range flights and resulted in a range of just 497 miles. With a top speed of just under the speed of sound, this meant it could only carry enough fuel to fly for around 45 minutes. As with many other experimental aircraft like this one, only one Stiletto was ever built, which conducted a total of 51 flights. It was never meant as a production model, and while it highlighted a number of issues with a design like this, elements were taken and incorporated into other jets, like the F-104 Starfighter, that went on to be an important multi-role aircraft for the U.S. Air Force in the 1960s. Number 2. The Avro Vulcan. The Avro Vulcan was a legendary British bomber aircraft that played a significant role for the country during the Cold War era. Featuring an aggressive and distinctive wing design, it still wows audiences to this day when it flies over at air shows. The aircraft had a delta wing configuration, which is a triangular-shaped wing that extends from the fuselage at a straight angle. Now, this design choice is a particularly important one for aircraft capable at flying at subsonic speeds while needing to carry a heavy bomb load over long distances. Now, rather than being a pure delta wing, though, the leading edge of the Vulcan's wing was slightly swept, which helped reduce drag and improve the aircraft's performance. This feature allowed it to achieve its operational speed and range requirements. Furthermore, despite its relatively compact size, the Vulcan had a relatively large wing area, which provided the necessary lift to support its heavy bomb load, and actually allowed it to carry up to 4,000 pounds of armaments over its 1,600-mile range. With a single vertical tail fin positioned at the rear of the craft to provide stability and control that was lost by the wing shape, it was powered by 4 powerful turbojet engines that were housed in underwing nacelles. The positioning of the engines beneath the wings allowed for efficient airflow and reduced the risk of engine damage from foreign object debris during takeoff and landing. While it is an uncommon type of wing to choose for a bomber and one that came with disadvantages, there were a number of benefits to the Vulcan's Delta that contributed to its effectiveness as a strategic bomber. Firstly, it allowed the Vulcan to achieve high subsonic speeds, making it difficult for enemy interceptors to catch or target effectively. And secondly, the large wing area and efficient aerodynamics gave it the range necessary to conduct these long-range missions, including strategic bombing runs and reconnaissance. Additionally, despite its speed and size, it was also known for its stability and control, which were essential for precision bombing and reconnaissance missions. Number 1. The X53 Active Aeroelastic Wing. The X53 Active Aeroelastic Wing, also known as the Adaptive Compliant Wing, is one of the most ambitious experimental aircraft ever created, and it was the result of a partnership between NASA, the U.S. Air Force, and several others. The X53 project was developed to investigate the potential advantages of adaptive wing technology and their implications for aircraft performance. And to do this, they designed the most adaptable and smartest wings ever. At first, they may look like any other, but it's far from being a typical fixed-wing aircraft. The first important thing about this wing is its flexibility, as rather than being rigid like on most other aircraft, the use of advanced materials in manufacturing allowed for the wing to deform and change shape in response to varying flight conditions. It's known as adaptive for a reason, and that's because it's able to actively alter its shape during flight with the aim of optimizing performance. And this adaptability hinges on the use of actuators and flexible composite materials that provide precise control over the wing's shape, including its camber, twist, and span-wise curvature. At the flip of a switch, the wing can be shortened and adjusted in just about any way by rearranging the slats that it's made of, meaning it can take on a completely new profile, as when mission requirements needed to do so. This, of course, gives it a number of advantages and means that it's able to fly just as effectively at low speeds as it can at high speeds. Another consequence of having such an adaptable wing is that it actually reduces the overall weight and structural complexity of the craft, because by eliminating conventional control surfaces like flaps and ailerons, the X53 achieves weight savings while still maintaining precise control over its performance. It was first flown in 2002. One X53 was built as part of the project, and it was the first full-scale proof that an active aeroelastic wing was possible. Quite how far the project has developed since then isn't entirely clear though, and this is still seen as a potential future of high-speed and highly maneuverable aircraft design. So when it's more reliable and affordable, it'll likely be incorporated into a next generation of military jets. I'll see you guys next time. Thank you to our channel members.